Hi, Margaret.
Hi, Mr. Walker.
You get some of your crazy amount of work done?
Yeah, some of it.
Yeah.
Actually, well, I had kind of like a huge emotional breakdown on Saturday.
Uh-oh.
Just like freaked out. And just like everything was making me sob uncontrollably. So I got like basically nothing done Saturday because it was just like freaking out emotionally. That's happened
Yeah.
like twice this semester. It never happened before. Like it's
Yeah.
so weird. But yeah, I'm doing a lot better now. So yeah, I did catch up a lot on Sunday. Sunday was very productive.
Yeah. Sorry to
So,
hear that was rough for you.
yeah, oh well, it happens. Yeah. I was sitting in class in another class right before this, and I was doing some portraits. I don't know if you can see those.
Oh, they're great. Yeah.
Yeah. So just
Excellent. That's a good way to
trying.
take the brain to a more
Yeah.
relaxed place.
Yes. Definitely trying to draw out
Nice.
all the stress
Nice.
now.
Nice.
Having some weird, like, slow internet connection problems today. So if I disappear today, I'm gonna try my best to get back in. But I was having some trouble earlier, so just a
Okay.
heads.
Thanks. Samvit, are you able to hear me? Hello.
Can I come hang out with you?
Of course. So I've already got Margaret logged in and Samvit, I think. I haven't seen him yet.
Do you know the order that they logged in?
I'll try to ask. And Fort Worth Country Days now joining. Margaret, do you know roughly when you logged in? Oh, Margaret, you wouldn't know whether Samvit was there when you logged in or not, would you?
Yeah, some of it logged in right around like 2:00.
Do you know if you were in and then he next, or vice versa?
I think I came in and then he came in maybe
Yeah.
like a minute or so after me. So I came
Okay,
in at 1:59.
Yeah, I've got an administrator here with MSON that's trying to trace back an issue that of figuring out someone's not showing up on the video when it's being recorded, and she's wondering if it has to do with when they're logging in. So I'm checking on that. Hey, Fort Worth Country Day, how you guys doing? Good to see everybody. Can you guys drop your camera angle just the smallest little bit? And yeah, we can't go in any tighter, can we? Yeah, that's about perfect then. Okay. How's the weather over in Fort Worth these days? I'm guessing pretty warm. Let me guess the temperature, like 85 or something?
It's getting there. Definitely.
Yeah. That's the high for today, 85.
Nice! Look at that. I didn't even check the weather. That was a
Okay,
shot in the dark. I'm going
Mr.
to
Walker,
guess. Go ahead.
I have a question about my presentation. Okay, so I'm doing nicotine, and
Don't light up in class.
no, I wasn't going to. Okay, but isn't this the one? Okay, is this not the project where you want us to do like a demonstration of it, or is that our final project?
That's the final one.
Okay, the question.
Yeah.
Never mind.
Yeah. No, so yeah, we're doing demos for something totally different. Hey, Samvit. Samvit, can you share your presentation with me? Okay. Thanks, buddy. Looks like I got it now. Thank you.
That's some bit login.
That's Easter's.
Yeah, Mr. Walker.
Yeah.
If I put a TED Talk in my presentation about nanobots, would that be acceptable?
Yeah, let's see. So it's someone else's presentation that
Well, like 3 minutes of it. I could cut the video down to be less than 3 minutes though.
So no, then it's not your words, and it's sort of like if you did a paper where you did, you know what I mean, like half the paper was someone else's cut and pasted words in it. So do you feel like, what is it in there that's critical? Are there images that are critical, or?
No, I just thought it was a really cool example because I was going to talk about nanotechnology and then like the potential applications, and it's a video about engineering hydrophobic molecules to make waterproof coatings.
So here's a question for you. Would it make more sense to send that to the class beforehand so they could watch it, then they could watch your presentation or listen to your presentation and have that background knowledge, or would it make more sense to see it afterwards? To me, if you've got 5 to 7 minutes allocated and you took 3 of that to show someone else's, you know what I mean? Then you're down to 2 to 4 minutes of a presentation from Casey. Do you see what I mean? So I think you can think it through, and it might make a lot of sense to do it, send it to the class, but I'm not sure it makes sense to make it part of your presentation.
Could I, if I have editing technology and I can just do like a 10 to 15 second clip, would that be acceptable?
That sounds more appropriate. Then you could say, yeah, this is from something else. And does that make sense why I'm saying it that way?
Yes.
Okay, so I think that might make a lot more sense to do it that way, because otherwise we lose your voice and then we only hear, or we hear a majority of someone else's voice.
Okay, I can do that. Thank you.
Great, thank you.
I'd like to go first today or second.
Sambit, I'm ready for you first. Is that good for you?
Hey, Robin, are you going to school? Are you going to college in Switzerland or here in the States?
Actually, I'm not entirely sure yet. I'll see. Yeah.
What are you thinking? Do a lot of people from your school go to college in the States, or I guess you do it online high school? Never mind.
Well, the online high school is located at Stanford, so most people are in the U.S. So most of them do go to American colleges, but I'm still, as I said, not really sure.
I'd add in also that I also go to the same school as Robin, and we do have people that apply to schools in the UK as well as in the US. But yeah, since everybody's, a lot of them are in California, and the people who are, if you're sending things to, or if you're sending applications to the US, I think the people in California are the ones reading it. There's a California representative, so that's kind of like where the school is technically based.
Okay. Wait, Margaret, where are you going next year?
Where am I going to? Well, I'm a junior, so I don't really know.
Okay. Junior.
How many seniors are in this class?
Hi, Maya.
Is Maya junior or senior?
Maya is a junior. Right, Maya?
Yeah.
Yeah, and I think everybody else is a senior, except for Margaret, Maya, and maybe I don't know who else. Robin.
Yeah, Robin's a junior too, I think.
Junior. Yeah.
Wait, Summit, are you a junior or senior? I said or.
I think he's a junior.
So are you a junior or senior? Because that didn't help.
Salvados.
Am I allowed to DJ until class starts?
Yeah. Hey, Maurice. Maurice, where's Chandler?
Teacher call.
He's where?
Teacher call.
Can't hear you. Oh, there he is. So far, they've logged in the order they're shown. So 1, 2, 3, 4, 5, 6. Hey, Max, welcome to class.
How are you, Mr. Walker?
Well, thanks. How are you?
Doing well.
Okay, gang, we're closing in. My clock just rolled over to 2:15. And let's see how we're doing on numbers. We have 4, 5, 6, 7, 8, 9, 10, 11. We're missing Olivia. And I think I knew in advance that Olivia was going to be absent. Okay. So, Maya, thank you for the tunes, but we're going to now ask for those to go away. Thank you. It's a good way to start class. I'd encourage everybody to come in and hang out from 2 Eastern Standard Time till 2:15 when we start, and we'll have Maya play us some tunes and relax a little bit and chat over things. Thanks for folks that came in and are all set to go. What's the question?
I just don't know if I'm in the. Is our video working? We're just not seeing.
I believe our video is working. Can people see Max and me? Yep.
Yeah.
So for some reason we can't see ourselves, which we're not too worried about because picture in picture.
You can actually do it here.
Oh, in there.
Yeah, so if you do this one, I like picture in picture.
Oh, let's get rid of that. Max, there you are. Look up. Because then that blocks Maurice and Max. You see yourself up there? Max.
Yeah.
All right, now we're out. Okay, we are going to start off with a presentation from Samvith, who is talking to us today about LEDs. And Samvith, is the best thing for us to do to open your presentation that was just sent to them by email? Samvith.
Yes. Yes,
Okay.
do that.
Can I get everybody to open the presentation that I just sent you guys by email? I sent you 2 today, one for Samvith and one for Maurice. And are you planning to talk us through the slides today, Samvith? Samvith, your mic is muted. Please unmute it. Are you planning to talk us through the slides today?
Yes. Does the push to talk thing not work?
What's the push talk thing?
I can mute my mic, and I press spacebar to push to talk.
You have to
Okay.
hold the space bar down.
Oh, yeah, that's right. It's not instant. Okay, this isn't TeamSpeak. Okay.
Okay, so why don't we wait for everybody to give us a thumbs up. This means that we have Samvith's project presentation in front of us, and we are ready to go. Maya, are you good now? Okay. Samvith, if you would just be so kind as to tell us next slide, or make sure it's very clear what slide you're on so that we don't interrupt your presentation, that would be great. Are
Yes,
you
sir.
all set? All right,
Yes.
great. Well, go ahead
All
and
right.
begin. Thank you.
All right, so the LED, unlike my previous presentation, is a lot less harmful for starters. The LED is short for a light emitting diode. You see it a lot in home improvement stores, in computers, etc., etc. If you advance the slide, you'll see that the LED, short for light emitting diode, is basically a newly emerging type of light bulb that is gaining ubiquity in the lighting and in basically general electric sphere. The goal of the LED, as the name suggests, is to, well, light stuff up. However, in a much better way than incandescent lighting. I'll explain that why. For now, and please enjoy the image as used in electronic schematics of an LED. It hints to what an LED is made of. Advancing the slide, the LED, although it is only a trending item, has been around since the start of has been around since the turn of the 20th century, where English scientist H.J. Round discovered the phenomenon known as electroluminescence. And electroluminescence, in a nutshell, is essentially saying that we can basically fiddle around with electric charge and the discrepancies in electric charge to release light, just as in a similar vein to a electron moving between distinct energy levels in a nucleus is electron is orbital. When it moves in distinct stages, or when there's a large enough discrepancy, that change from one level to another will release light in the form of photons. Moving forward to 1927, former Soviet inventor Oleg Lozev basically built the first LED, and it was not until 55 where American inventor Reuben Brownstein basically used gallium and arsenic, put them together to form a semiconductor, and basically created an LED that emitted infrared light. Now, infrared LEDs in the context of general lighting are not very helpful because infrared lighting is invisible to the human eye. However, at face value, the infrared LED is used for things like TV remotes. But moving forward, it was not until 62 where it was Nick Holonyak that was able to create the first successful visible light LED. Because LEDs from the gallium arsenic semiconductor came infrared, it was through several attempts at tweaking the LED that came about to forming the red light. Moving the slide, we see where the semiconductor comes from. Basically, in the area known as the lead frame, the anvil and the post, you have what is known as a PN junction, which, short for positive-negative junction, is the area responsible for creating that light that comes from the discrepancy in charge between the positive and the negatively charged sides of the LED terminals, respectively from the anode and the cathode. The cover of the LED, the epoxy lens case, etc., can be made of a variety of different materials, including the aforementioned gallium, arsenic, indium, and sulfur, as well as silicon, to create a variety of colors such as red, blue, ultraviolet, well, really fancy purple, and white. Especially noteworthy is that in the modern context, LEDs are able to be white because the epoxy lens case is made from like a phosphorus layer, and that phosphorus layer turns the light white, which then can be modified to turn red, green, or blue. Moving forward, the LED is able to the versatility of the LED basically compared to a incandescent light bulb is cheaper and is a lot more energy efficient. Consequently, it costs much less money to operate an LED compared to an incandescent light bulb when comparing two bulbs that produce the same amount of light. And as a result, because unlike incandescent that uses basically a heated filament to emit light, the LED does not have such parts. And as a result, it is less susceptible to quote-unquote burning out and consequently lasts much longer. And because the LED, coloring the LED can be made through less hazardous materials, compared to a CFL that uses mercury to achieve the same light effect, LEDs are much easier to dispose. Moving the slide, one must remember that not everything is perfect, and that LEDs, similar to how new technology forms, is initially very expensive. But it's worth mentioning that because it's not an incandescent light bulb that radiates the heat from the filament inside the incandescent, the heat within the LED stays inside. So in order to take care of that, many mainstream LED manufacturers have put heat sinks, like the one shown in the picture at center right. Moving forward, because of the merits of the LED, one can find it pretty much anywhere, from custom-built PCs to cars to TV remotes, hence the aforementioned infrared light, explaining why the light in a TV remote, if you stare into it, is invisible. But if you take a picture with it while using the TV remote, you'll see a little red dot because the camera can pick up infrared light. And finally, moving forward, advancing the slide, LEDs, aside from the ones shown previously in how LEDs work, can also take two other forms. The OLED, the organic light emitting diode, basically uses, well, an organic compound, such as in this case ALQ3, which stands for aluminum tris organic chemistry name. I'm sorry about that. Another much more recent form of LED that has been showing up is the quantum dot LED. And with respect to the standard LED, with regard to color, the quantum dot uses, well, quantum dots, which in themselves emit their own light, compared to a standard LED, which needs phosphorus to turn white, and then in the context of TVs, where QD LEDs are being frequently seen nowadays, QD LEDs emit their own light, producing much more accurate color reproductions of an image. Whereas in a standard LED, you use the phosphorus covering to make it white, then you use the various aforementioned chemicals to make the RGB color spectrum to achieve the image reproduction as necessary. In summary, advancing the slide, LEDs are a fairly new technology that remained idle for a century as incandescents gained ubiquity, primarily because since incandescents were easy to develop, LEDs were to airplanes. LEDs were to airplanes then. I'm sorry. Let me rephrase that. LEDs were just about as foreign as airplanes to in the turn of the 20th century. So as a result, they were not developed. They were pretty far out then. Now, because lots of R&D has been spent into them, they pose a eco-friendly and viable alternative to incandescents. Because they can be made so small, their versatility increases by orders of magnitude compared to an incandescent and a CFL. And because of its long life, simply put, it is the way forward. I end my presentation there.
All right, let's give it up for Sunbit. Okay, I think Joel has got the first question for you, Sunbit, and then we'll take it away for others. Thanks, Margaret, for waiting. Joel?
All right, so you did a really good job, Sunbit. You answered most of the questions I kind of had. So I had to come up with another one on the spot. What is the wavelength for it's the different wavelengths that determine the color of the light. So what's the wavelength for green?
Green, 500 to 550 nanometers, something along those lines, because visible light is between 400 and 700 nanometers. So
yeah,
if I remember,
it's between 500 and 570. So you got it.
Okay.
Noise.
Can we try this? What is this picture thing where you can see the light, the blast and whatever the.
Max. So we're gonna go to Margaret and then Max. Margaret first.
I was just wondering if you, if you were aware that a Nobel Prize in Physics was actually awarded for blue LEDs, and if you happen to know who was attributed to having sort of invented the blue LED, which came much later than red and green LEDs.
I did read of something. There was a fairly big discovery to have blue LEDs, but off the top of my head, I don't remember the person who was credited with such a prize.
Yeah, it was actually like a group of people. So like a lot of names I can't pronounce: Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura.
Okay.
Yeah, no worries about that, but it was cool.
Max, I think you had a question.
Sunbit, please explain to me what this thing is with the remote. You said where it shows up and you take a picture, like the infrared light shows up. I've never heard of each.
This is how it works.
Yeah, that was
okay.
Cool.
Let's see if this mouse emits infrared light. Okay, so similar to a TV remote, because it emits infrared light, and because infrared light is essentially invisible to the naked eye, what one can do is take a smartphone camera, I guess in this case, let's say the latest iPhone, because I know that thing can. You basically take a picture of it while you're basically operating the device. So in this case, the TV remote, like pressing a button, it'll emit an infrared signal, and the image sensor the image sensor of the iPhone can pick up infrared light. And basically, once you take a picture and review the photo, what you'll see is a red dot coming from what you normally see as a little glass bulge thing from the remote. And basically, that red bulge, that red circular area, is infrared light. It should work.
But it's not working. Help me.
Okay. Okay, then I'm a doofus.
Help me.
I don't know.
So
Wait, so should I point the remote at the camera?
Yeah, try doing that.
What I would imagine is possibly it sends out such a weak signal that your camera's going to have a hard time picking it up unless you either had some way to make the exposure long.
We need
or...
to go back and picture the picture because I've been messing with where the camera's pointing. Wait, how do we go back to the?
Are we all mixed up?
I would assume so.
No, we're okay.
Not that bad.
Yeah. All right. Other questions for Sumvit? Thanks. Let's go to Chandler and then Maurice.
I had a question about the organic LEDs. You talked about the benefits of the quantum dot light emitting diode, but you didn't. I was wondering if there are any benefits to organic light emitting diode.
Organic LEDs, like quantum dot LEDs, they can lead to a better color. They can lead to better color reproduction, and I only speculating here, but the fact that it's organic can suggest a more eco-friendly process for both creation and disposal.
All right, Maurice?
Yeah, and I had a question about the LED itself. I was wondering what the wire bond connecting the anvil on the anode side to the semiconductor die is for.
The wire connecting the anvil to the semiconductor die, huh? I'm staring at the diagram, and I see it as a continuous piece of metal. I don't understand what you're asking.
Oh, I see the wire he's talking about. There is a wire. It's called wire bond that seems to.
Oh,
link
wire bond. Okay, well, okay. Well, because the anode, and again, only speculating, unfortunately, but because the anode and the cathode are not physically touching, electrons cannot move from one end of the anode to the cathode. So it's apparent that there must be a way for the for basically the potential difference to move from one side to the other. As a result, the wire bond, I assume, accomplishes this task, and consequently, through the electroluminescence phenomenon, allows the LED to light up.
Great, thanks.
Thank you. Robin.
I had a little bit of lag, so I hope I'm not asking something that's already been answered. But one question I had was sort of, you said that an LED will be damaged much less quickly than a general light bulb that we have today or a CFL. And what are the processes by which it can be damaged? So that was sort of my question. Is it also sort of the wire that can burn, or what are sort of the reasons for it being broken? So yeah.
Okay. So to reiterate, you're basically saying what are the causes for LED damage?
Yeah.
Okay. Robin, to answer your question, remember back to when I said that LEDs, unlike incandescents, do not radiate the heat they emit. So that's one possible source of error. And if you go to the slide labeled quirks and trade-offs, you look again at the LED that basically has the little bars around it. That's the heat sink, which basically simulates the radiating excuse me, of heat from the LED bulb to the outside world. As a result, the LED is actually quite cool to the touch, which is part of the reason I found them quite interesting when I had them installed in my room. But that's a different story. Again, another source of LED damage is, well, physical damage, but that was self-evident. And I think that's about it. I mean, the main risk in normal operation is simply heat dispersion and making sure that it's dissipated properly.
All right, Max got one more question, then we're going to probably have to end it there.
How an incandescent light, like every once in a while when you turn it on, it'll just kind of blow out. Is that the same thing as the heat radiation and like equivalent in LED? Is that what happens where it just blows out? Not like explodes.
Please repeat the question.
I mean? You know, in an incandescent light bulb, like every once in a while, I'll just turn it on. I have a couple in my room. I'll turn it on and it'll just like get really bright for a second and then just die. Like it'll just kind of blow out.
I think I know what you mean.
LEDs, or is that due to some engineering in the incandescents?
Well, to answer your question about the blowing out, what happens in the incandescent, from my understanding, is that basically as the current flows through the incandescent light bulb, when it crosses the filament that's responsible for heating up and creating the light associated with the incandescent, the filament will wear out over time as current passes through it and time goes on. So it'll reach a point when the filament basically cannot handle the current that's flowing through and will consequently just kind of like start just blow out a light and then fade out because, well, it's broken. An LED does not do that, but I do not know how necessarily an LED dies. Let's see. Yeah, unfortunately, I do not know how an LED dies. I suppose that parts within the LED can malfunction as time progresses, but because there are fewer parts that are more susceptible to this kind of error, the LED is able to last longer.
Got it.
All right, let's give another round of applause for Sambit. Thank you, Sambit. Excellent job there. Okay, we're going to go on to Maurice and your presentation. Maurice, do we do the same thing? Do we load up the slide, or do you have an actual, remind me, do you have a video we're going to watch?
No, loading up the slides would probably be the best.
Okay.
That's what I hear.
And Maurice, are you talking through it as Sambit did, or?
Yes, I am.
Okay, so I got to get rid of this one. Why are you not going away? There you go. So can you guys load up Maurice's presentation on opiates, please? And can I get just a thumbs up from people once they've got that set? I'm all good. Sambit, are you good on that one? Okay. All right, Maurice, you've got it. Take it away.
All right, great, thanks. So if you can just move on to the next slide, I guess. First, I'll start off with a definition of opiates. An opiate is a narcotic analgesic that directly depresses the central nervous system. Analgesic is a pain-relieving medication, and we'll kind of get into more types of analgesics and how they work later. So if you go on to the next slide, we investigate how do opiates affect the brain. Opiates act straight on the central nervous system to relieve pain. Opiates attach to the opioid receptors, which are found in the brain, spinal cord, and many other organs in the human body. When these drugs attach to the receptors, they reduce our perception of pain. In this diagram at the bottom here, what we see are receptors on the target neurons, which, as I said, are located in the brain, spinal cord, and other organs. And what we have are these opiates that attach to the receptors, and they have similar conformation to naturally occurring enzymes in the human body. If you guys can move on to the next slide, we investigate how opiates compare with other pain medication. Opiates and traditional pain relievers, such as NSAIDs, aspirin, ibuprofen, Tylenol, they all work in very different ways. Tuning receptors, which interact with COX-1 and COX-2 COX-1 and COX-2 enzymes in the human body, create waves of pain. Over-the-counter drugs work by blocking all pain-signaling COX enzymes indiscriminately, generally, preventing them from interacting with the nervous system, which in turn creates pain. Various types of over-the-counter drugs work in different portions of the metabolic pathways that lead to the COX-1 and COX-2 enzymes binding to these tuning receptors. And opioids, however, work in a completely different way. They don't have anything to do with blocking of the COX enzymes, but instead they work by blocking the transmission of pain signals to the brain and by binding to these opioid receptors you guys saw in the previous slide. Next, if you move on, we have investigate different types of opioids. An echoanalgesic chart is a morphine-centric chart that compares the general strength of different types of opiates. Just as something that I found was interesting, morphine at similar dosage to NSAIDs was about 116th as strong. NSAIDs were 116th as strong as that of oral morphine, and aspirin was about 1/360th as strong as oral morphine. And there are three different types of opiates. There's natural opiates that occur straight from the poppy plant, which you have morphine and codeine. And there's semi-synthetic opiates that are derived from natural ones. We'll investigate several types of synthetic opiates in the coming slides. And synthetic opiates generally very, very strong and high degrees of pain relief and binding to the opiate receptor are directly derived from the lab and bind to the opiate receptor. If we move on to the next slide, we see two examples of naturally occurring opiates. First, we have codeine, which is an opiate used for its depressant, analgesic, sedative, and hypnotic properties. Along with morphine, codeine is the second most common opiate in opium. And generally, codeine is used to treat mild to moderate pain, as it's around 1/10 as strong as morphine. And morphine is the main psychoactive element in a chemical in opium. And morphine is an opioid analgesic drug as well, and it is primarily used to treat severe pain. It appears to mimic endorphins, which are shown to be responsible for analgesia, sleepiness, and feelings of euphoria. They can be released in response to pain, strenuous exercise, orgasm, or excitement. All these other drugs work in similar ways. These two on the next slide are semi-synthetic opiates. Hydrocodone is a semi-synthetic opioid synthesized from codeine, and it's a treatment for post-surgical pain that is generally moderate to severe. As a narcotic, hydrocodone relieves pain by binding to the opioid receptors in the CNS, and in blood, about 20 to 50% of hydrocodone is bound to protein. And it's about as strong as orally ingested morphine. Diamorphine, which is known by more commonly as heroin, is also an opioid analgesic synthetic one made by adding two acetyl groups to morphine. And surprisingly, I found this was kind of interesting. Heroin was sold by Bayer, just like aspirin, on the market. Sold on store shelves for a very long time, and was used as a substitute for morphine. At the time, it was thought to be much less addictive, even though it was later found to be obviously more addictive and more powerful. On to the next slide, what we see is two fully synthetic drugs, fentanyl and carfentanil. I thought both these drugs were very cool at over 50 to 100 times the potency per gram as compared to morphine. Fentanyl is a potent synthetic opioid and historically has been used in surgical procedures as a pain relief and as well as an anesthetic in combination with benzos, which are benzodiazepines, which are pain relievers. Our carfentanil is the most potent opioid known to man, and it's generally used as a general anesthetic for large animals, and it can be as much as 10,000 times as strong as morphine, which is pretty incredible. If we move on to the next slide, I kind of go over some medical applications here. It's generally used to treat breakthrough pain pain that cannot be treated by other medicines that block COX enzymes. Instead, opioids, as I mentioned before, generally treat the perception of pain rather than the pain receptors themselves. And it's used in post-surgical pain, chronic pain, cancer pain, as well as codeine, which is much more mild. It's generally used as a cough suppressant. So you see that in cough syrup. And it's essential in proper pain management. If we move on, a major topic about opioids is abuse and recreational use. Recreational use and abuse results from the fact that opioids create an acute sense of euphoria and create a warm, satisfied feeling in the user. Opioid abuse has extended way back all the way to when poppy plants were first scored and their sap collected for morphine and codeine. A dangerous aspect of opioids are that they're highly addictive, and higher and higher quantities are necessary to realize similar levels of euphoria. And thus, as you may imagine, this can be very dangerous. So opioid antagonists such as naloxone and nalextrone target the opioid agents and change their conformations so they can't bind to the opioid receptors. And they're treated and they're used to treat opioid overdoses. Opioid overdose depresses the respiratory system as well as the central nervous system, which can lead to death and coma. So if we move on to the next slide, just as a conclusion, opiates are used for pain management as they alter our perception of pain. Actually, I had surgery a little while back, as you guys may know, and I took hydrocodone mixed with acetaminophen. And this combination targeted two different pain pathways. The COX receptors were blocked with acetaminophen, which is kind of an OTC drug, and hydrocodone blocks my perception of pain by binding to the opioid receptors. Yeah, so that's the presentation. So thank you guys.
Good job. Okay, I think Willie has your first question for you.
I do. Earlier in your presentation, you mentioned that there were some naturally occurring opiates in the body, enzymes. Do you happen to know any of their names?
Yeah, the nalextrone binds to the opioid receptors. Endorphins and dopamines inside our brain, they also bind to similar receptors in the neuron in the either the brain, spinal cord, or other organs in the human body.
Wait, did you say endorphins? Is that what you said?
Yeah.
Oh yeah, that's what I was looking for. All right, got it right.
Good job. All right, good. Other questions for Maurice? Samvit. Samvit, you're muted.
Maurice.
Yeah.
Maurice. Yeah, the push to talk thing is being mean. Maurice, you kept referring to the chemical COX and COX-1, COX-2. What does COX stand for?
Let's see. Well, I actually do not know off the top of my head what COX stands for, but they are enzymes found in the body. So.
Okay.
And that's totally fine. Other folks, let's see, Chad? No?
It's Joel.
Joel, sorry, I mixed you guys up. Joel, yeah, I got you.
No, it's good. So you talked about like how it blocks the pain, like how it stops pain, but like, is that what causes the euphoric feeling, or like what people would call the high, which like causes the addictiveness, or is it like, are there other ways in which it causes like the euphoric feeling?
That's a good question. So it's not actually the blocking of pain that causes the sense of euphoria. It depresses the central nervous system, and that's really what causes the euphoria. It just kind of alters our perception because opiates themselves don't block pain. in the strict sense of the word, because what they mostly do is it's the COX enzymes and the OTC drugs that bind to these COX enzymes that actually reduce pain. Opiates they depress the central nervous system and affect our perception. So that's kind of what creates that sense of euphoria.
Other questions for Maurice? I'm going to look for others. Joel now. I'm sorry. I did it again. Chad.
Yeah, I'm Chad.
Yeah.
Why is it that greater doses are necessary to achieve the same amount of euphoria every time someone would take opiates?
That's a good question. Like if you think about bodily resistance, it's the same kind of thing for insulin and diabetes, type 2 diabetes. Like if you take more and more and more sugar in your body, what happens is these molecules desensitize to the receptors desensitize to these molecules, and thus you need more and more. You need to flood the body with more of these opiates in order to achieve the same effect. So for type 2 diabetes, for example, more and more insulin needs to be injected in order to compensate for the receptors being unable to kind of accurately process insulin. So in a similar way here. Endorphins are also processed not as well by the opiate receptors.
Other questions for Maurice? Let's see, Rob and then Margaret, and then I have one.
Also, another question is, what is really the reason for sort of overdose leading to, say, breathing problems, etc.? Is it just that your nerves are somehow restricted, or what would be the reason?
Yeah, so essentially, with overdose, you're depressing the central nervous system to a level at which you cannot carry out normal bodily functions, which is primarily the biggest problem would be respiratory failure. And it also depresses heart rate. It also depresses and thus pulse and all sorts of other bodily functions. But respiratory problems are usually the first thing that hit.
Margaret, you're muted, Margaret.
I'm sorry. I'm trying to do the same thing that some are doing and having equal difficulty. So I'm interested by the molecular structures of these opiates, and so it makes sense to me that codeine and morphine and hydrocodone and diamorphine all kind of have the same sort of backbone with three hexagon-shaped groups or something. So my question to you is, do you know why the fentanyl and the carfentanil seem to be structurally very different looking than these other molecules? Are they binding to different proteins or different receptors? Is that why?
That's an interesting question. Given the fact that carfentanil has about 10,000 times the potency as morphine, I would expect so. There's actually two different types of opioid receptors in the brain. I don't really know them off the top of my head, but there are two different types of receptors. And my best guess is that these two bind to receptors that codeine and morphine and other semi-synthetic opioids are not conformationally able to bind to. So that's my best guess.
Chandler, I'm asking this partly of you, but I'm asking it sort of your classmates as well. I'm projecting your slide of codeine and morphine. Do you understand what the line structures, like clearly there's some atoms shown, there's O's and C's and A's. Do you understand what the line bond structures are representative of? Or could you explain that to your classmates, I guess, is part of my question?
Yeah, so essentially the hexagonal structure, is that hexagonal?
Yes.
Or hexagon? Yeah. Hexagon. So what we have is double bonds when you have those two lines.
You're doing great. Keep it up.
Yeah. So what we have is double bonds At each of those junctions, what we have is carbon atoms. It's a carbon backbone. Let's see.
Okay, some of your classmates have had organic chemistry, and some of them have done it with me. Others may have picked it up from other sources, but for some other people, just looking at that, it may not look like you're dealing with a molecule, but it's an organic shorthand for a bunch of carbons, and each, as you said, each single line represents a bond between two carbons, and a double is a double, and anything that's extra from that, like nitrogens, are shown, and then there's some shading to show coming out of the ring structure, that kind of thing.
And then some of the other directions indicate bond angles.
Right. Excellent. Good. I just want to make sure people knew that. Any other quick questions before we move on? Samvit, thank you.
Yes, push to talk worked. Okay, a question for Mr. Walker and/or Maurice. In the slide containing fentanyl and carfentanil, although it was discussed how the structure of each molecule could contribute to being synthetic, my question is how in both molecules in the diagram it depicts like a lone carbon single bonded to another carbon, like in fentanyl moving at I think top middle right there's like a lone carbon, and then in carfentanil at like center right, top and bottom, there's like lone carbons. Does that suggest that both molecules are charged?
Well,
or not
Maurice
charged,
try.
but rather.
Maurice can try, and I know Margaret will know the answer because she's at organic with me. So, Maurice, I don't know if you know, but go ahead and try.
So the question is, the fact that two carbons are single bonded to each other means they're charged?
Margaret, take over with that one. Help answer the question.
I think I can answer the question. But
Okay, sorry.
I'm just trying to clarify. What was he saying that? What was the question?
Basically, there are lone carbons on fentanyl and carfentanil. What does that suggest about the molecules? Are they charged innately, or are they still neutral, or what is it doing?
So they're not charged. They either are double bonded to something else, or have hydrogens bonded.
See, that's the trick. In this shorthand notation, hydrogens are just not shown; they're assumed to be there. So when there's a single line, it just means a carbon to a carbon, and what is not shown is just a bunch of hydrogens. So some of it's an excellent question, but it refers to a shorthand notation where hydrogens are just left out because an organic chemist would know how many would be there. Really good question.
Okay, that makes sense.
Yeah, really good question, and that's the kind of question I want. I know when you present structures like this, if your audience doesn't quite understand how to interpret them, that makes it tough. So that's why I wanted to ask my question, and I think your follow-up question is excellent too, to making sure everybody understands better. So thanks for that. Any others? Okay. Thank you, guys. And let's give it up for Maurice again. Excellent. Well done. Because of the Easter holiday weekend and Passover, we weren't able to get all the presentations ready for today. And also Olivia was going to go today, and she's absent. So we only have 2 presentations today. So we're going to kind of do a little bit of double timing as we move forward to get through our other presentations. Let me say to Samvit and to Maurice, I want to encourage you guys to head off to YouTube, not until class is over, but as we go into the weekend, there'll be other people that are doing final work on their projects. If you guys could go hit the YouTube and start doing finding some fun videos out there, that'd be great. I think the best thing for us to do in terms of our time is to pick up with our conversation from Disappearing Spoon. So I'm hoping that folks are okay with that. Because I feel like going between now and when the author shows up, we're mostly going to be working through the presentations that you guys are doing, and you're doing a wonderful job with them, so thank you for that. And as Samvit and Maurice showed today, you can do a nice presentation either through the slides and just talk it through, or you can do the presentation, by doing a video that you provide in advance. So thanks for you guys for your work on those and becoming the many experts in different disciplines. you guys are teaching me things too. I certainly don't know all the things that you're describing, and am not an expert on those. So thank you. So how about, I think last we had talked about chapter 11, how elements deceive, and I think we're ready to go on into chapter 12, unless any of our conversations have sparked interest or questions that go back into previous chapters, but I think we're ready to go into chapter 12 now. And I believe many of you have updated me in terms of where you are in the reading, but I don't think everyone has. So please let me know where you are in the reading if you feel like you're in that category that hasn't updated me. So chapter 12, I wrote a little side note. It's called Politics, or it's about politics. I don't remember the exact title. It's Political Elements, so I guess pretty close. And I have some notes here that I took when I was, doing the reading. Anybody want to start us off on a discussion of chapter 12 and what you found interesting on chapter 12 or want to bring up? Casey, that'd be great. Thank you for starting us off.
I thought the section on Marie Curie was really interesting, and how she named polonium after Poland, which wasn't a country yet, but then it ended up being a completely useless and rather dangerous element, and it didn't get the coverage she wanted. So I thought that was kind of sad, but I thought it was a very interesting story.
Yeah,
just to add
extremely.
On, I thought the whole story about Marie Curie was really sad. Just how well she did, and then her husband died, and then she died, and how they kind of focused more on her personal life than on her science, and then her daughter died from leukemia. It just I don't know. I mean, she obviously was one of the greatest chemists to ever live, and made so many advances. But it was it was not a great way to go out, I feel like.
Definitely, and it shows that a lot of what we've learned is on the backs of people that have certainly suffered and their families have suffered. So yeah, excellent point, Willie. What stood out for other folks? Maurice, thanks.
I thought it was interesting how they renamed hafnium to protactinium. Just the difference in the naming is just kind of funny.
Yeah, the whole bit about naming is definitely interesting, and there's certainly a lot of history in a lot of that. Anybody else with a comment? Robin, thanks for taking it.
I think that just sort of this revocator idea of sort of drinking things with uranium inside them being healthy, I think that just sort of one thing that really shows how science develops and how it also helps our society. So also considering, for instance, those uranium watches and how they influence, say, the workers who produce them and so on. I think both of these historical symbols sort of really show us how science can develop society in great ways.
Yep, Max.
I just didn't really understand that part about the revogators, I think it was called. Was it drank because they thought it was healthy because it looked, they're saying a translucent green, because I didn't get what it was because it said it was some sort of I think it said a health drink of some sort of, what sort of health benefit did they think it had
I don't know if anyone can help Max out. I certainly can't help with that. I wouldn't want to drink something just because it was glowing or green.
I don't know. That was just the only thing that I thought it was just people. So I don't know. I was posing that.
I'm trying to not say anything because I don't want to spark the conversation, but I've got some things. So Margaret, thanks. I can ask questions, but.
On the revogator note, I think it's very strange that there isn't much of an explanation other than it just says, it's a health tonic, but I don't see a whole lot of justification for that. But it's kind of funny how, in a related manner, we've got things like tracers that you do swallow, and we do use the radiation for medical purposes. So it's kind of like the same idea, but being applied in different ways. One's okay, this is really weird, doesn't make a whole lot of sense. In the other case, it does. So it's kind of interesting, the parallelism there.
Yeah. So I found this story fascinating, and I'm horrible with names, so I apologize for screwing this name up. But Grigori Hevesy, and when he was suspecting that his landlady was putting the leftovers back out the next day. What did the knucklehead do? That
was awesome.
Oh my God! Right? What was the background there? What did he actually do to determine whether or not he was getting Willie?
He put tracers in the meat, and then she cleared his plate to see. He said he wasn't hungry, and she cleared his plate, and then the next day, oh, you had hamburgers yesterday. Well, now we're gonna have beef stew or whatever, and he saw the
lead. Radioactive lead. Can you imagine?
My favorite part about that was that the landlady was just like, "Yeah, you got me." Wasn't mad about it because she just got busted in the craziest way.
Yeah,
and also.
Go ahead.
I also thought it was crazy with Hevesy, because he kind of started to coin this science about tracers, and then he ended up drinking heavy water to see how long the average water molecule stays in his body, and he just pretty much peed into a bucket for a couple days to figure out when it was all gone. I thought that was pretty interesting.
Yeah. It's hard knowing what we know now about radioactivity and things that are dangerous. And then looking back, and people just didn't know. There was a time I feel like it was the 50s, but it sounds odd that would be true, when you could walk into a dime store, which is what they called a drugstore back then, and you could literally walk up to this place to try on your shoes, and you could put your feet in this device, and you could look down and see the bones in your feet through the shoes as a way to determine if they were on or not. So you were basically looking at x-rays of your feet, and you could walk into a store and do this. It was like a device that was there. People had no clue that how dangerous this stuff was when they used to do this kind of stuff.
Even
so
mercury or something that used to be a toy.
Mercury, yeah. People used to play with mercury. I've seen videos on the internet of some guy sticking his finger in it, just, again, done back in a time when there's just a lot more... less care about certain things. Samvit.
But, Mr. Walker, it's important to not forget that the 1950s, especially 1950s America, post-war, early Cold War, however you want to put it, was basically a almost golden age in chemistry and physical science in general. We basically had discoveries in the nuclear field showing up left and right.
Totally right. Yep. Do you guys know what aqua regia is? It was mentioned in the book at some point. AQUAREGIA. Maurice knows, and Casey. Maurice, what is it?
Let's see. I'm not 100% sure, but it's a solvent. That can dissolve gold.
Good. Yeah, it's a mixture of nitric and hydrochloric acids, and Hevesy used it to dissolve his gold Nobel Prizes, and then you can reverse the reaction using other reagents, but it was a way of keeping it away from the Nazis, which I thought was incredibly interesting as well. Other comments from anybody? Don't want to shut down. I think that's about it then for chapter. Oh yeah, thanks, Maurice. Go ahead.
It's Chandler.
Oh, sorry. Yep, you're right. Chandler.
Yeah, I thought the whole Nobel Prize deal was a little weird. How a lot of the times they weren't awarded to as the best science at the time, but it was just whatever made the best political decision. And I know that's something that happens a lot in the world, but I thought the Nobel Prize would be a little better than that.
Yeah, you would, and unfortunately, history gets in the way, and politics gets in the way, and even someone being Jewish gets in the way. I mentioned Lise, I think is probably how you'd say her name, Meitner, who should have co-won the Nobel Prize in 1945 with Otto Hahn, and again, she had Jewish grandparents, and that was enough to make it so that she wasn't part of that whole thing. So it's messy and it's ugly, and that's part of our history. Anything else from 12 before we go into 13?
The tragedy of Joliot Curie.
Yeah, do you want to comment any more?
I don't know. I was just like, because I mean, it just kind of extends. There's like a it's not an irony, but it's I don't know, maybe a coincidence that it just the same thing repeated itself, like chemical discovery, tragedy, the chemical discovery, then tragedy.
Yeah, I hear you. All right, how about chapter 13? I wrote down it essentially deals with money. I don't remember if it had an interesting title beyond that, but it was definitely dealing with money and currency and different elements. Elements is money. Okay. Anybody got anything cool there? Margaret?
Okay, I read this one, but I don't remember any of this.
Yeah, I hear you, Willie. That's why I take notes, because I can't remember this stuff without a few notes to look back at.
Didn't realize the microphone was on.
Yeah. Gotta love the ability to pick up minute sounds in this room class.
Okay,
Casey.
when I was
sorry, Margaret and then Casey. My bad.
Okay, I just wanted to say that actually, this whole section, I actually did a little bit of a lab related to this chapter about Midas, and there's like some suspicion that the bronze is actually just copper that has formed an alloy with zinc, and you can basically do this with a penny. So you can actually put it in a solution, get it down to the zinc, and then wait a second, am I thinking of the right order? But basically, I've done this in the lab before, and it's pretty amazing how gold the penny looks. You know, it's a pretty convincing reaction. So I could relate a lot to what he was talking about.
Cool.
We did this lab earlier in our AP Chem class this year. It was cool. We what did we do? We soaked it in zinc, and then we heated it up on a hot plate, and it goes with the copper and turns into bronze just like immediately, or not immediately, but like it goes from like being silver to being gold like really quickly. It was cool.
Yeah. Yeah.
It's funny. The hardest part was though we had to gather all these pennies that were from before 1982, because after 1982 all pennies were made of zinc instead of copper, so we had to find like pure copper pennies. Yeah. It's cool.
Casey, do you still have your point?
Sorry.
Yes. Oh, I thought the part about counterfeiting and how it used to be easier to counterfeit coins than it did to counterfeit paper money. I thought that was fascinating because it's something you don't think about these days because we all have access to paper and printers.
Got you. Yeah. Robin.
Also, it was kind of interesting to read about, and also amusing to read about this aluminum story, how it became sort of this really huge deal and more important than gold to a great extent. But always keeping in mind the loss of value that we've experienced today, that you get aluminum foil everywhere, etc., versus gold foil, for instance, is extremely valuable. It's very interesting to see sort of how also these things develop over history. So
yeah, I don't know if you guys are familiar with Oberlin College, but Charles Hall went there, and it was there that he discovered that process of getting the aluminum from its ore changed the world, changed history, and he did that at age 23, founded American Aluminum Company, Alcoa, which is still a company going strong. There's a 6-pound cap on the top of the Washington Monument made of aluminum. That I knew about that, but put there in 1884, back when it was worth so much. Other things, there's a really cool thing in this chapter that no one's mentioned yet. Jad?
Joel.
Just kidding, Joel.
Just say the opposite of whatever you're thinking.
I know, right?
I'm not sure what the real cool thing you're talking about, but I just wanted to mention where it talked about iron pyrite, and like it kind of goes along with the counterfeiting, except this one's a little bit easier to tell, but it would still like fool people that are searching for gold and think that they had it. And when I was little, my brother had a huge thing of it that would sit like on his bedside table, and I of course thought it was real gold and had no idea how he had a huge rock of real gold. And then when I like finally figured out that it was like fool's gold or whatever, but it does have like a really amazing shine to it.
Yeah.
That, it talks about like how it's almost a cartoonish shine, like what you would expect, and it really is.
The thing I'm thinking about is the Australian town where people were basically tearing the town apart rock by rock, ripping out parts of the What was going on there? What did they find they could do with the rocks in that town?
Couldn't they like get the gold out, and they used all the materials they used in the buildings? Actually, they discovered later after they built the entire city actually had gold in it, and so they ended up destroying the city to get more of it out.
Gold is so unreactive that when it's in an ore, all you have to do is heat it. It's called roasting, and it just rolls right out as pure elemental gold. So once they figure this out, they do literally start tearing the town apart, and as maybe any of us might do when they figure out that was happening. So crazy stuff. The last thing I thought was really cool before you guys leave is europium is in European bills, EU. I thought that was kind of cool. Do you remember, because of the light that hits it and it phosphoresces back out? So kind of a cool little thing there. Anyway, all right, we see each other again on Monday. Some of you guys, I might send an email to help you with this, but some of you guys are not participating enough in class.
We see each other on Thursday.
I see you guys on Thursday. Today is Monday, yeah, so we see each other on Thursday. Some of you, we want to hear your voices more. Others of you are doing a great job of that. Who's got a question? Samvit, you got a question?
Yeah, I was wondering why you corrected yourself, but I was wondering why is there no class on Thursday?
Because I'm an idiot. I thought it was Thursday today. I'm thinking ahead already. So I see you guys on Thursday. Take care.
Bye.
Good job, folks that did presentations today. Maurice and Samvit. Excellent.
Did I do better?
Yes. Good job.
Thanks.
Thank you very much, Mr. Walker.
See you Thursday.
Bye.